I used math to fix a mistake in the original Sherlock Holmes. In The Adventure of the Priory School, Sherlock Holmes and Dr. Watson come across a pair of bicycle tracks. Holmes instantly knows which direction the bike was headed, and when Watson asks how, he says, well, what he says doesn't entirely make sense. Holmes can tell which track was made by the rear tire because it carries more of the rider's weight and left a deeper impression in the soil. But even so, if each track stretches out of sight in both directions, identifying the tires doesn't tell you which way the bike was facing. This is often regarded as a mistake in Sir Arthur Conan Doyle's writing. The annotated Sherlock Holmes by William Baring-Gould had this to say: "Much, perhaps too much, has been written about these tire tracks. Holmes' deduction has been challenged by Galbraith and Rand, among others, defended by Blakeney and Gardner, among others. But it is clear that the tracks would look the same both ways unless the tread had some lack of symmetry or other peculiarity and the manner of mounting it on the wheel were known," Mr. Galbraith wrote. Mr. Blakeney wrote, "In any case, Holmes probably had a dozen other small indications to guide him. Though he might mention only one factor, he usually had others in reserve." So the question is, was there a way that Sherlock Holmes could have deduced the bicycle's direction of travel from only its tracks? My answer is yes, using math and geometry, even if the tires had symmetrical tread or none at all. All we need is to examine a place where the tracks turn or even slightly deviate from a straight line, which in the story, Holmes confirms that they do when he says, "You perceive several places where it is passed across and obliterated the more shallow mark of the front one." I mean, you can hardly ride a bicycle without sometimes turning or wobbling a little bit. That's how you stay balanced. Anyway, Holmes's method for identifying the tires doesn't work on pavement. If the tracks are intact, my method will work on any flat terrain. The answer lies in the physical properties of a bicycle. There are two wheels, only one of which turns. The back wheel stays parallel with the frame, while the steering axis of the front wheel is in about the same place as that tire's point of contact with the ground. What this means is something very important in terms of geometry. By definition, all points on the front tire's track must lie at a fixed distance along tangents of the rear tire's track in the direction of travel. I'll say that again. All points on the front tire's track must lie at a fixed distance along tangents of the rear tire's track in the direction of travel. Remember, a tangent is a straight line that's parallel with a curve at the point where the two of them intersect. And of course, a bike frame is a straight line, and it does keep the two wheels of the bicycle at a fixed distance from each other. So a bike frame is basically a physical object that enforces that geometrical relationship. And that geometrical relationship essentially describes a bike frame. In fact, this provides enough of a model for how bikes move that I used it to write a simulation. Given one tire track, defined by the plot of this arbitrary equation, my simulation creates the track for the other tire. Here it is simulating backward, that is, from the front tire to the rear tire. So you can see the arbitrary equation is providing the front tire, and my simulation is providing the back tire. And now here it is simulating forward. So the arbitrary equation is providing the back tire, and my simulation is providing the front tire. There we go. So, using this model, we can tell a few things even at a glance. Number one, the front tire always has longer curvature than the back tire, and thus tends to be on the outside of the curve. Incidentally, this leads us to the curious conclusion that a bicycle's front tire travels a marginally greater distance than the back tire on average. Number two, for abrupt turns followed by relatively straight sections, the gap between the tracks will be wider at the back and narrower at the front. You can see that on both of these. So it kind of looks like an arrow pointing in the direction where the bike went. Or maybe a Nike swoosh or something, but that's the longer point points in the direction of the bike. And number 3, the bulge of the front tire track tends to favor the anterior side of the turn, almost as though it's a bubble in a hose that's been pushed in the direction of travel. Here we have an aerial photograph of some real bicycle tracks. Now, when we approach a set of tracks like this, there are 3 variables that we don't know. 1 is which track was made by which tire. 2 is which way was the bike facing and traveling. And 3 is how long was the bike frame / how far apart were the tires. Now, what our model that we described before, what that provides us is a definitive way to test combinations of values for those 3 variables to see whether they are correct or not. And it also provides us some at-a-glance indications, like we mentioned. For example, we can see immediately there's one of these tracks that tends to swing on the outside of the turn and has longer curvature. That's probably the front tire. And we can also see the gaps between tracks where one side is wider and the other side is longer and thinner. But let's not get ahead of ourselves. Let's try to test the model as rigorously as we can. So let's pretend we don't notice those things. And let's sort of start with assuming this might be the back tire. Well, does it work? Let's see. If we pick this point, for example, right here, this point right here, and we draw a tangent here, well, immediately we can see it does not intersect in this direction. It only intersects in this direction, which means if that's the back tire, the bike could only be facing this way. But there's a problem. If we test here, at this point, now we have the reverse situation. There's no intersection in this direction, and it only intersects in this direction. So if this is the back tire, now it could only be facing this way. Well, it can't be both because the bike didn't magically reverse directions in between these 2 points. The tracks show no evidence of that. So this can't be the back tire. It has to be the front tire. Let's erase these marks. All right, so our model has definitively confirmed what we saw at a glance, that this is the front tire and this is the back tire. So let's focus on this as the possible back tire here. Let's take this point here and draw a tangent from here. Let's try to be careful with our angle here. Now we can see it intersects in 2 places, here and here. So one of these is about, we'll say roughly 3/4 of an inch. We're working with some error margin here. But the other one is only 1/2 an inch. So if the bicycle is headed this way, then the frame is 3/4 of an inch long on this paper. But if it's headed this way, then it's 1/2 an inch long. Well, let's take another point and see which one is correct. Let's take this point here. All right, now we have another 2 intersection points. Right here, and all the way over here. Now this one, that's still just a little over 3/4 of an inch. Depending on, some slop. But this one, that's like over 2 inches. Well, it's almost 2 inches long. So there's only one direction here that stays consistent, and that is this direction. So our model has given us a definitive answer that this bicycle was traveling from right to left, and that on this printed sheet, the frame was about 3/4 of an inch long, roughly. And this turns out to be the correct answer. So there you have it, a general solution for determining the direction of travel if you find bicycle tracks. And I'm not going to say that Sherlock Holmes got it wrong, but I kind of think Sir Arthur Conan Doyle did. What do you think? Let me know in the comments below. Thank you so much for watching, and if you liked this, please hit the like button and subscribe. See you around. So, special thanks to my friend Victor of Aerial Image Solutions for the drone shots in this video.
Absolutely. Thanks, buddy. I appreciate you including me. It's a lot of fun.